My name is Chris Chambers. I'm the client support manager at Meter Group and the Teros product manager.
My name is Jeff Ritter. I'm their product manager for our plant, canopy, and atmospheric monitoring instrumentation.
So we're here to answer a few questions today. Hopefully we can help out. And if you have any future questions, be sure to send them to us. Okay, so our first question is kind of a transmission option question. Can ZENTRA Data Loggers transmit on a LoRaWAN network? Or when will this be available?
Yeah, so our data loggers are currently transmit over a cellular network. So they're not currently enabled for LoRaWAN. We're working on some other technology to expand those capabilities over Wi-Fi or maybe even in the future over a radio mesh network.
And there's a lot of ins and outs and what have yous with the way you deliver data, right? And generally, our philosophy is, however you can get it to the cloud. But LoRaWAN does have some data limitations. It's generally short snippets of data that you're bursting, right? So maybe it's something we'll have for the future. Right now, it's not one of our priorities.
Right, especially when you're talking about really data-rich instrumentation, like a weather station.
An Atmos 41.
Exactly, an Atmos 41. The more sensors you add on there, the more limitations you run into with the low data networks.
All right. Okay, how about installing power sensors? Do you have any suggestions for power sensor installations?
The biggest thing with any sort of sensor that's measuring radiation is to get it level. Incident radiation is going to be hugely impacted by the angle of incident light. So if you don't have it horizontal to the surface, you're not going to be measuring accurately. So that's the biggest thing.
And do you have a general rule, like how far, like what's good enough as far as leveling radiation sensors?
Typically within 3 degrees of dead level is what we would suggest for those. But then again, closer to 0 is better for more accuracy.
More level is better.
That's right.
Okay, moving on. How high can a chain link exclosure be? And I think the better question, or maybe the more relevant question, is how high should a chain link exclosure be? I'm gonna just do some top-down processing on this.
There's a couple of things to consider. What is the exclosure trying to exclude? If you are trying to exclude deer, for example, they can potentially jump a 6-foot fence. So if it's for cattle, they're probably not going to be able to get over a 6-foot fence. But the height of that exclosure can potentially also impact your weather station. So you need to keep in mind what your application is for. If you were trying to adhere to World Meteorological Organization standards, that weather station is going to have to be pretty high compared to any obstructions that are around there. So you need to keep that in mind, what you're trying to keep out, as well as what you're trying to measure and for what purpose.
How high, as a general rule, say if it's an Atmos 41, how high above the exclosure do you think it should be?
That's a good question. Typically, you want it, if you're measuring ET, you want it 2 meters above the canopy. Right. So keep that in mind with your exclosure, how high that needs to be so it's not impacting what you're measuring there. If it's a WMO station, I think the recommendation is 10 times the height of a nearby obstruction.
Oh, goodness. That's pretty high if you've need a big chain link fence. Let's skip over to sensor recalibrations. Okay. As a general rule, and let's focus on Atmos 41s, since that's what we do. How often should you recalibrate sensors?
Yeah, so there's recalibration and there's maintenance, right? So if you're talking about just recalibration, the sensors that do need to be recalibrated should be probably every 2 years. Okay. We typically recommend every 2 to 3 years, and those are the sensors that can drift. So specifically something like a relative humidity sensor or the pyranometer, those can drift over time. So to make sure that those are within the published accuracy spec, we say every 2 to 3 years for those.
Great.
Now maintenance is a little bit different, where that's going to be site specific. If you've got this station out somewhere where there's a lot of detritus from the atmosphere, a lot of leaves, or if there's a lot of bird activity, you get a lot of bird fouling on the station, that can prevent precipitation flow, or you can foul your pyranometer and then degrade that measurement. So maintenance should potentially be at least yearly, but depending on the site, every couple of months even.
And so if you suspect your data isn't great, you might need calibration, but it's not 2 years yet. Do we have any tests or anything that we can recommend a client do to check on it, or standards?
Absolutely. And again, there's a lot of measurements being made on the weather station, so each one is going to be unique, each verification. The biggest thing is getting out and doing a site visit and making sure that it's clean and everything is working properly. But then we do have methods for verifying the accuracy of your precipitation gauge, for example, and the other sensors on there as well.
Right. There's always that bird that wants to just perch on the funnel and
that's right.
Right down in
if
there.
If a bird has made a nest in the funnel, you're going to have skewed data. So
bird spikes.
Use your bird spike kit.
Here's a tricky one. If I have no other option other than mounting my wind sensor on a roof, what do I have to consider in particular to get acceptable data?
Well, I mean, in general, you're not going to be getting, the same wind speed as you would on the ground. And so you just have to accept that. There's not a lot you can do if you're mounting this way up in the air. The environment is very different up there.
Could be some turbulence and that you wouldn't normally see in a field or something like that.
That's right. Conditions on the ground are going to be very different. And so if that's your only option, it's better than not having those data, but you just have to live with that error. But
I assume get it up a certain height above the roof, probably.
That's
get it
right.
on the peak and not
and
on
make sure that there's not any obstructions around. On the top of a roof, it's very easy to have things in the way that you might not think impact the wind speed because you think it's far enough away, but
chimneys or HVACs. Or
that's right. All that stuff
like
can play a big role in what you're seeing. So again, even if you have it on top of a roof, you want it several meters above the rooftop.
Right. So the question from our live studio audience is should we take a reference reading, like on the ground or something like that, to compare to the roof?
I think that's a good idea to get a general sense. I don't think, with the variability of wind speed, I don't think you'll ever be able to, say, calculate a correction factor doing that. I don't think you'll get that level of consistency and precision.
You'd have to have it there all the time.
That's right. And in that case, they're already saying that's not an option in this case. So it's not a bad test, though, if you're measuring wind speed on the ground and you're measuring it over a course of a couple of days and then compare it to what it looks like up on the roof, you can at least say, we're at least this far off.
Right. And it probably depends on the questions you're asking as well.
Absolutely.
Okay, how do you level an anemometer? And each anemometer is going to be slightly different. The Atmos 41 has a couple of options, doesn't it?
That's right. Yeah. So the easiest way, and any high quality instrument is going to have some sort of built-in way to level it because of how important that is, especially if you're using something that expects you to be horizontal, say a cup anemometer or a two-dimensional sonic anemometer, like what's on the Atmos 41. The expectation is at your level, so you're going to introduce errors if you're not. So with the Atmos 41, there's a built-in bubble level. There's also an accelerometer built into the instrument, so then you can check all the time. You've got a data readout exactly of how level you are, and so you can actually see when your instrument has fallen over or just tilted out of spec.
Which way do you prefer, personally?
When I'm installing it, the bubble level works the best.
It's just right there.
But then I also keep a readout typically in my remote data of what the accelerometer is outputting, so I can be alerted any time that the station might tilt outside of that spec, so I can flag those data for exclusion.
Great. Oh, the ever classic site selection. When faced with a less than optimum location, like say urban settings, is it better to site the anemometer 5 to 6 feet above a rooftop peak or at the top of a 5 to 6 foot ground pole? We've addressed this a little bit in a previous question about roof mounting. And this really depends on the questions that you want to ask.
Absolutely. Yeah. Depends on what you're wanting to look at. So it's hard to say in general, but if you're in an urban setting, that typically means you're going to be looking at some sort of impact on human comfort.
Or ecosystem services, possibly.
Right. And so I would lend more towards having it closer to the ground, because that's the microclimate that you're interested in. But again, it's going to...
Sometimes the roof is the best you can do.
Yeah, absolutely.
The next question kind of harks back to our exclosure question previously, and crop production inside cages, presumably to protect them from browsers or birds or something. How would you position the device to minimize the interference from that?
Right, and I think as far as like evapotranspiration is concerned, so the thing to keep in mind when you are measuring evapotranspiration, or in this case, when you're modeling evapotranspiration, is that's what we're doing with most weather stations.
Right.
It's not a direct measurement of evapotranspiration, but it's a modeled value. So you already are simplifying a fairly complex process.
Right.
The specific implementation of that model, what we call FAO 56 in the way that Atmos 41 does it, is a further simplification of that model. So if you were to take that and you start playing with some of those other parameters, like putting this under your canopy or under a cage, you're going to introduce more error into that measurement. So one of the beauties of that modeled evapotranspiration measurement is that it's actually a model of the reference or the potential evapotranspiration, not directly what that plant is doing right next to it.
Right.
So in order to understand what your plant is doing as far as evapotranspiration goes, you need to understand a little bit about your plant and how it's interacting with the environment. And that's done through what's called a crop coefficient. So if you can get a sense of what the crop coefficient is for your plant in cages or out of cages, or however, you can apply that to your reference evapotranspiration value and then adjust it that way.
And would it be just as well to use like a reference, like not that crop, but a reference crop nearby, like if you've got a grassy area or another crop that's not covered? Would that be helpful at all? Or
using the crop coefficient from that crop? It depends. Crop coefficients can be very dynamic from one crop to another, but even over the course of a growing season, they can change. So you do need to have some information about your specific crop and how it grows. And in that case, you would want your weather station out in as we would typically recommend, out in a clearing.
Yeah, gotcha. How to correct the air temperature measurement? Let's back up. How do you correct the air temperature measurement due to solar heating from sunshine?
Right. So this is a good question in that the Atmos 41 does this automatically already, because anything you put out to measure temperature is going to be impacted also by the solar radiation load.
That's why we see radiation shields on passive devices.
That's right.
Yeah.
So you need to have a measurement not only of the solar radiation, but also how much heat is then lost back to the environment through cooling. So you need a measurement of the wind speed.
Right.
So if you measure both solar radiation and you understand a bit about the solar absorptivity of your temperature sensor, and you're measuring wind speed, you can actually come up with a correction factor to correct your air temperature. So that's what we do in the Atmos 41. And what we actually see is it is closer to what we would call an aspirated shield, a air temperature sensor that has a air current flowing over it.
Which is typically the gold standard for air temperature measurements.
Right. It is closer to that than, say, a passively radiated, a passively shielded sensor. Because those are also suffering from solar radiation causing temperature increases.
And the Atmos 41 measures everything that you need to do the correction. So
that's right. And it's all built in right into the data output already.
So this is kind of crop specific. Our next question is crop specific. I'm not a banana crop agronomy expert, so maybe we'll just stick to the biophysics of this question here. If you're very limited in space and the only area available to install the station will have a 30-meter diameter canopy around it, but it's unobstructed. Is that going to be enough to give you good data for your, say you're doing a reference ET measurement?
It depends on, I don't know the height of a banana plant, but yeah, if you can get it up high enough, it should be able to. If you can get 2 meters above the canopy.
What's the minimum that we recommend have like a space, like a fetch for, or an area of influence for the Atmos 41?
Typically, WMO standards say 100 meters away from obstructions.
Okay.
But again, a lot of ET measurements, we aren't necessarily adhering to WMO standards in the first place. That's just kind of best practices if you can. So trying to avoid the obstruction as much as possible. And even if it's not a perfect measurement, it's better than just guesswork.
Okay. So to boil it down, 100 meters would be ideal, but 30 meters is probably enough to get you some good information.
I would imagine so, without knowing specifics of bananas.
Okay, great. Can the Atmos 41 fail to record rainfall data? Anything can fail to record rainfall data.
Yeah, and there are 2 main methods that it can cause problems there. Aside from some sort of a catastrophic failure, like your weather station is struck by lightning and the circuitry is off right. The main modes that it can cause really almost any weather station to fail to record weather precipitation data are if the pathway is clogged, if a bird has built a nest in your funnel, you're not getting rain through there to measure in the first place. But also there are limitations on if the station isn't fully level. If rain isn't getting into the funnel, or if rain isn't flowing through the correct pathway because the station is off level.
And this isn't unique to the Atmos 41. If it's missing the drip counter or if it's missing the bucket.
Yep. Anything that alters that path that the water flows can impact that.
That's right. And here's the tricky thing, because rainfall, precipitation in general is crazily, maybe not stochastic, but it's highly variable spatially, right? And so to, just as an anecdote, we had a softball game on one end of town and it dumped on us here. The softball field was only a mile away, right? And they hadn't had a single drop. So here I am just taking it easy, assuming the game's going to get canceled, and they were going to play. And so I was late to the game. Everyone was mad at me. But
and we see that a lot with people who see a rainfall event, and you want to compare one station to another one that's miles away, and rain just is not that homogeneous in how it falls over an area.
Even over a couple hundred meters, you can get large differences.
You can get huge differences in that rainfall event.
But we do have a method to double check your rain gauge, right?
Yeah, and it's something that I suggest people to do all the time is check your rainfall gauge. We've got a published method for how to do that. It's fairly simple. You just essentially pour a known amount of water through. And that's a great way to have confidence in your measurements.
Right. Will ZENTRA Cloud eventually facilitate additional metadata? Yes.
Sure hope so.
It has to someday. It's on the list.
Yep.
Which sensors and where should they be installed to complement hydric measurements at tree level?
Yeah, so there's, you've got to understand that there is a continuum of how that plant exists from the soil all the way up into the atmosphere.
Right.
And so you want to make sure that you are able to monitor not only what's happening in the atmosphere around that plant, but also what's happening in the soil. So understanding the water content of the soil with soil water potential sensors or water content sensors is important. And for where to install those, you want to have them down at the root zone. So you need to understand how deep your plant, or if it's a tree, how deep do the roots of that tree grow?
Now, what about something like a vapor pressure deficit? Suppose you're doing a sap flux study. That's going to be one of the major variables if you're for your evapotranspiration. Any thoughts on that?
Yeah, so you can get vapor pressure deficit directly from the Atmos 41, where it's measuring vapor pressure and temperature. If you want to get vapor pressure deficit specific to the leaf, you'll need to measure leaf temperature. So you can do that with something like an infrared thermometer measuring canopy temperature, and you can get VPD that's specific to the leaf itself.
Oh, great. Any tricks to keep stations running when they're experience power drops? Let's take a moment on this one, because power management of data loggers, you've got a ZL6 data logger, self-contained solar, rechargeable batteries, and you've got a bunch of sensors on it. And what really throws a wrench in the works frequently is cellular communications, right? Any thoughts on when you should watch out or take steps? Or there's got to be some balance of how much power is being used by the cell modem versus how much light you can harvest, especially if you've got your canopy, your solar panel shaded.
Yeah, you're right. So the first thing and the easiest thing is to just make sure you're in an area that's got good solar exposure. If you do that, you should be okay. If that's not possible, you're right that the cellular communications is the biggest power draw on most loggers. It takes a lot of power to communicate. So making sure that you have an area with a good connection, and you test that before you finalize your installation.
Right.
And potentially using some sort of an antenna on there to boost that signal. That can be a big help to make sure that you're not spending excess power trying to send data remotely.
And if you are experiencing power problems, contact support. We're here to help.
That's right.
Does reference ET work in ZENTRA Cloud now? Yes. Yes, it does. What kind of care must be taken to install a station on a glacier surface?
Well, first off, you've got to realize the limitations of your weather station. If you are using a low power weather station, it probably does not have an onboard heater, because that's a big power hog. So if you don't have an onboard heater and you're putting this someplace where conditions are consistently below freezing, some of the measurements aren't going to work. Precipitation. If you get ice buildup on some of the sensors, that can include your measurement pathway.
Also, your glacier surface is always moving.
So you need to make sure that this is secured in a way that you are comfortable with, and not falling over.
You might want to get some alerts for. Can we set up alerts for, say, the onboard accelerometer?
Yes.
So that if it gets out of level, it gives us a.
Yeah, you can set up alerts so that you get a text message or an email if your station ever tilts.
Assuming you have cell coverage and cloud access.
That's right. The thing to consider is that, and this might be a smaller issue, but saturating vapor pressure as calculated over ice actually uses different coefficients in the Teton's formula than it does over water. And so you might need to do some post hoc data calculations to correct for that. But
cool. Is the bug in your API solved? Yes. Let's journey into our virtual weather portion of today's broadcast. So come with us, gentle listener. And first off, what do you think about virtual weather? First of all, what is it?
Sure. So virtual weather is, we were talking about models a little bit earlier, and virtual weather is essentially taking broad scale weather modeling and reducing it down to a grid level, so you can get essentially predicted weather at any location using some pretty fancy statistics stacked on top of those models. So it's really powerful. It's great for looking at broad scale questions if you don't need great resolution or extremely high accuracy at those resolutions. And like anything, it depends on what question you're asking to see how useful it's going to be. I'm a big fan of using satellite and remote sensing applications, using model data when you can, as long as you understand the limitations and how important it is to ground truth those.
So let me get this straight. Say you've got a nearby regional weather station that's like 5 miles away. that you're getting precipitation from for your farm. The idea is that you're you're trying to find some way to estimate whether your specific location is always like 3 millimeters behind that one, or 0.5 millimeter, or you get more rain in your specific locale.
Essentially, okay. Yeah. It's trying to create grids at those scales from stations that are either farther away or just from overall weather mapping models.
How well does it work?
I've seen some that say on certain days they're within 2 degrees. Sometimes I've seen them as far off as 4 or 5 degrees as far as temperature goes. So for the scales that a lot of people are looking at, that's pretty good. But once
then
you're
talking about averages then, right?
Right.
So
once you start getting down to really complex topography, or if you get into applications where it really matters, even a couple degrees off can cause huge implications if you are a grower and you are trying to look at weather inversions or cold air drainage. It's not going to work for that.
Or if your max is actually 5 degrees off, your vapor pressure deficit is going to be, you're not going to capture that in the average.
That's right. So we've got a weather station here at our building that's kind of at the top of this little hill, and I've got one down, just a few hundred meters away at the bottom of this hill near a little river that we get some cold air drainage down there that, even into the summer, I was seeing freezing temperatures down there that would not be captured in a virtual weather forecast. And that can impact, not only the fauna that wants to move through there, but, the sort of plants that are going to grow there and how they grow there and how happy they're going to be. It's going to impact pest management, disease management, et cetera.
Right. And finally, for this segment, current state of the science. Do we think virtual weather will improve substantially, or will we always need local weather stations for accurate forecasts?
Yes to both. I think that absolutely, models are continuously improving. The more data we get, the more computational resources we have devoted to those. Those are going to improve, but I don't foresee ever having the sort of coverage that we would need for complex landscapes, especially with how dynamic they are, to not have, measuring the actual microclimates that you're interested in.
And having the local weather stations, you can actually use the data to train your virtual weather station. So it does matter what you install your Atmos 41 over, right? The roughness of the surface. Say if you've got a canopy, you might see more. If you've got a rough surface, you'll probably see more turbulence, right?
Absolutely.
You'll probably see some different dynamics at it. Do you have any thoughts?
In general, it's going to depend on what you're asking. If you are wanting some measurement of the model values we've spoken about earlier, evapotranspiration, you typically want it higher above your canopy than that because of those, because of the impact that the surface can have. So I would say up to 2 meters.
Minimum 2 meters.
Minimum of 2 meters typically is what you want. That's what the evapotranspiration model actually uses, and you've got to correct the model if you use something other than 2 meters.
Right.
But in general, it comes to the question that you're asking. If you want a measurement in the canopy or close to the canopy, then that's where you should put it.
Get your sensor down there.
That's right.
The WMO and NWS have standards for the location and distances for weather stations and their sensor locations, right? Are there any standards for MediaNet or microclimate stations?
There are. The one that specifically comes to mind was published back in 2019 by the American Association of State Climatologists, specific to exactly this, siting standards for MediaNet weather stations. Now, a lot of that refers back to WMO guidelines. So if you are already using WMO, that should be fine for MediaNet scale work. But there are specific exceptions for the MediaNet approach that are laid out in there. So if you look for that from the American Association of State Climatologists, there's a good document on that.
Now, some of these, like the WMO specifically says that you have to keep your wind speed sensor like so far away from your station, right? But all that kind of breaks down with all-in-one stations that weren't even around when these standards were written, right? So how do you feel about people looking for WMO standards where the technology's kind of gotten ahead of the standard?
Well, it's great to have as a reference, you know, to look back on these stations that do adhere to that and say, okay, we know how good those measurements are. So if we can approach that with these stations that are currently slightly bending those standards a little bit in some way, and we can use that to make an argument that potentially in the future, you know, we can modify those standards. And so long as we have the data to back that up, I think that's a good way to approach it.
Great.
Yeah.
Would it be possible through modeling to obtain values of physical parameters such as temperature and humidity from inside the canopy using data from a station outside the canopy 300 meters away? There are for sure biophysical models that you can use to model, for example, wind speed inside the canopy if you're measuring it above. I'm not as familiar with looking at temperature or humidity models, though I'm sure that they exist. Probably depends on the canopy structure.
Probably, yeah. You'll definitely need to know something about the canopy architecture. Probably leaf area index is going to play in there to know how dense that canopy is. But you know, if you've got the right parameters, you can model just about anything.
Since ET is driven largely by radiation, is ET prediction closer using virtual data?
No. So we were talking earlier about how ET is already modeled by these weather stations.
Right.
And what are the variables that we're actually measuring for ET? It's solar radiation, wind speed, relative humidity, and air temperature.
Net radiation.
Yeah. Right, net radiation.
Right.
So, and it's right, that's a good point, where the ET model is using net radiation, which we are already assuming a value of that from solar radiation, incoming shortwave. So if we then start breaking that down even further and not using measured parameters, but using them taken from some other modeled source, you know, you're going to introduce more error into the system than if you're just measuring it locally. Right,
and it is such a driver of ET.
That's right.
In the system that
that's the one you really want to nail.
Yep. For an outside station used to estimate reference ET, do you get concerned about the local site dryness, if different from a well-watered grass, et cetera, on the ET reference estimates?
Yeah, that needs to be taken into account. Some further context for this is for reference evapotranspiration, for that model, it's assuming a closed canopy and a well-watered crop.
Right.
So if your crop is not those, you know, we already expect that reference ET is likely higher than what your plant is actually seeing, and you need to take these things into account.
And since we're not actually measuring the eddy covariance, then violations in the assumption are gonna really undermine the data.
That's right. You can take that into account, however, and a lot of people will, you know, look at ET and know how much they need to adjust it. Again, using like a crop coefficient, you can apply.
These are always fun. What is the best weather station density for 100,000 hectares? Is that 100,000 or a million?
You know, honestly, it doesn't matter if it's 100,000 or a million or even 1 hectare. My answer is always going to be the same in that I can't tell you. Yeah. It's going to be entirely application specific to where you are putting it. If I was to put this out on my grandparents' farm in rural Minnesota, I could probably put one of them on their 2,000-acre farm, and that probably describes the weather there pretty well.
But it also comes back to just good sampling procedures, right? You need a representative. It needs to be representative of what you're sampling. You need to have a large enough sample size to capture the variability.
But even that, the area of measurement of one of these stations is also dependent on the topography around it and on the weather conditions. So, if you've got a very complex topography, you want to be capturing that. You want to measure all those different microclimates.
Yep.
So it really comes down to what are the prevailing weather conditions and the topography of your site.
And what level of detail you want.
That's right.
Let's spend a minute on metadata because it's easy to overlook the importance of metadata. And just for an example of some metadata that's important, it's a little off topic, but definitely related for soil moisture sensors, right? If you're looking at volumetric water content, you really can't interpret those data unless you have some soil type. So that's one example where metadata is extremely important. And so the same things apply for weather stations. We've already talked about crop coefficients a little bit. So the crop that you've got, what other metadata should people collect specific to weather stations, and what do you see are some of the main things that get left behind that impact your data?
So one of the first things that comes to mind is having some sort of qualitative approach to looking at, especially in this case, an orchard, whether that's some sort of having a phenocam where you can draw information from, or some other way to look at the phase of what your orchard is in. So having that, I think, is really valuable in order to tie it to certain phases.
Well, probably slope aspect.
That's right. That's right. Getting back to having complex topography, it's one thing to just plunk your weather station down where you think the topography is interesting, but to actually quantify that and be able to have those as reference points. So you can say that I have this here, and it's facing this aspect of the hill. That's going to impact that. Absolutely.
Right. So can we say with enough confidence that local measurements are most relevant for modeling pests, diseases, etc.? And this probably depends on the model that you're using for pest risk.
I would say generally yes, but you're right. It depends on the model that you're using and what parameters specifically you're looking at. But for the most part, the ones that are very important in pest management and disease management are going to be air temperature, relative humidity. And those sorts of things are definitely better from local measurements. Absolutely.
Right. And microclimate's going to play a big role in this, as well as the overall weather patterns.
That's right. Yeah, microclimates are predominantly what matters to living creatures in those places, pests included.
And in that case, you're going to be more interested in what's happening like right down in your canopy than you are 2 meters above the canopy.
Yeah, those pests don't care what's happening above the canopy. They care about what's happening right there where they're eating your crop.
So let's pause and just look at the location of your station for a moment. And this is pretty specific. Is it better to leave a station inside a fruit orchard for more reliable growing degree days or evapotranspiration data?
No. So typically with the modeled evapotranspiration and those other models, there are, like we've discussed, some assumptions involved. And so you want those out, seeing the total solar radiation that's incoming. Otherwise, you're going to introduce extra error into those.
And your evapotranspiration needs to be positioned over a reference crop.
That's right. So if you are measuring, if you're able to measure evapotranspiration directly through, say, an eddy covariance setup, then yeah, you want those in there in your crop. But measuring evapotranspiration or getting modeled values of evapotranspiration, you definitely want to adhere to those recommendations.
And it depends on your model as well. If you need to have the microclimate, then it's definitely going to be best to be right down in your canopy.
That's right.
If you're looking at larger landscape processes, then you're probably going to be up and away from it.
That's right. Very application specific for your research.
So know what questions you want to ask. What is the advantage, besides using just one port, of the all-in-one ATMOS 41 versus separate sensors like the 22 plus the 14, the pyranometer, ECRN, and especially for ET assessment?
Right. So, you hit on one, and a lot of those play into that same reason. Using one port is for convenience. An all-in-one sensor, you can set those up in minutes versus versus when you're setting all of those up, that time adds up. Not only that, but data management is a big deal when you are pulling data from multiple sensors, and you are dealing with it that way. Also, having all those sensors co-located allows you to, when you are measuring ET and you say that these are all 2 meters above the canopy, they're all right there. You don't have to worry about any of them getting in the way of each other, having them all at 2 meters.
Air temperature correction.
The air temperature is corrected off of wind speed. That is the exact same location as the air temperature sensor.
Right.
So, it allows for a level of convenience and data management throughput that you don't get when you have your separate sensors.
Right. Could the TAMO weather station provide ET not? Yes. Yes, it can. It seems that all-in-one systems like the Atmos 41 can be teamed with ancillary power heated rain gauges or unpowered chemical snow melting gauges, right? Suppose you want total precipitation out there.
Yep.
But that is a separate sensor. The Atmos 41 currently doesn't have heating. It's just liquid precipitation, right? It just measures rain.
Yep.
So there could be other instruments used with the Atmos 41 to get you that snowfall precipitation or the total precipitation.
Absolutely. For precipitation, you're still going to run into a limitation if your pyranometer is covered, Atmos 41.
Right.
But if that freezing weather precipitation is important, then you will need to pair it with something else that has a heater on board.
Yep, that's right. So our next question is about kind of a precision irrigation question. And can you, for like high value crops, can you couple weather monitoring with soil moisture monitoring to back check evapotranspiration? And there's some quite sophisticated techniques to do that, particularly with the Teros 21 and Teros 12 together, where you're measuring matrix potential and water content.
Yep.
You can set your set points with the Teros 21, matrix potential. You know with the Teros 12 what your soil storage is. And so then it's not a very large jump to monitor your evapotranspiration and just refill the soil with what you've transpired over the previous day.
Right.
What does someone need to watch out for that? What are some pitfalls they might run into?
So that's a great way to do it. If you're measuring the pool of water in the soil and how available that water is, that's a great way to look at the water lost through the system. The biggest pitfall is that you're only looking at one very discrete location. So if you had 1 million soil sensors out over your field, you could monitor that. And so this is kind of where we get back to that question of scale. Are you using a satellite? Are you using a weather station? Or are you using ground sensors?
1 million sensors. I don't think you need 1 million sensors.
You probably don't need 1 million sensors.
I think you could do it with less.
You can do it with less, but there is a lot of heterogeneity in
there you go.
Water
Capturing,
so being able to integrate that into a more usable signal for your irrigation system. And so back checking that with soil sensors is a great way to see what's actually in the soil at that moment. And then you can use Atmos 41 modeled ET for that integrated signal.
The soil moisture sensors can corroborate your readings.
All right. Well, that's going to wrap it up for us. Thank you again for joining us today. We hope you enjoyed this discussion. And thank you again for everybody who has sent in such great questions. Also, if you have any questions that we didn't get to, please contact us via our website at metergroup.com. Finally, you can subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. So thanks again, stay safe, and have a great day.